Alright, welcome back to class. This is Mr. Brain, and based on what students have requested so far, we want to look at this topic, alright, hydrostatics. And we are solving questions, alright, questions, and we are hoping that at the end of this 8 questions, you have enough, idea, alright, or you are equipped with necessary instruments to be able to pass any test under this as regards to your what? Your Jamb examination. So let's start. Okay, so let's make the first question. We have a metal reel, alright? A metal of real weight, 10 Newton, okay? Weighs 8 Newton in water and 8.5 in a liquid, okay? The relative density of L is, so we are looking at relative density of what? L, okay? That's relative density of the liquid, right? Okay. Now, you need to understand that relative density has to do with what? The density of the substance, alright, over the density of equal volume of water, right? So when you compare the density of the substance to the density of water, that is what we call relative density. So now there are two things here. Number one, the metal and what? The liquid. How do we calculate the density of what? This liquid. Very simple. All we need to do is what? We look at, now we are comparing, now we are comparing liquid to water now, okay? So the metal weighs what? 10 Newton. Are you with me? 10 Newton ordinarily, that is 10 Newton in air. So when it enters water, it weighs what? 8 Newton. Then when it enters what do you call it? The liquid, it weighs 8.5. Alright? So if you want to get the relative density of that liquid, you're going to say the upplus in that liquid over the upplus in water. As simple as ABC, okay? So the upplus, why? Upplus simply means the weight that was displaced. The weight of the fluid that was displaced, or the weight of the substance. Yes, the weight of the fluid displaced, okay? So the weight of the fluid, of the liquid air displaced over the weight of water displaced. That will be the relative density of that liquid. So let's look at it. So what will be the displacement? The displacement will be the weight, the difference between the weight in air and what? The weight in liquid, and the weight in liquid is 8.5. So you have 10 minus 8.5. Please take note. This is weight in liquid, W. Sorry, weight in air is what? 10 Newton. Weight in air is what? 8.5. Are you with me? So weight in water is what? Weight in water is what? 8 Newton, right? So displacement in the liquid should be 10 minus 8.5. Displacement in water is what? 10 minus what? 8. And what do you have? You have, let's say 1.5 over what? Over 2. So 1.5 over 2, that would be what? 0.75. If I'm correct, 0.75. I hope you get that, right? I hope you get that solution, right? You can see that. Okay? So let's try the next question. Now it says a metal tube of size 0.2 meter suspended on a string is completely immersed in water of density 100 kilograms per meter cube. The upplus on the tube is, so we are looking for upplus on the tube. Now, please understand this. You see, the density of the water is 100 kilograms per meter cube. And now you are immersing a meter cube of size 0.2 meter completely. I get you. So the question is, what will be the upplus? What will be the what? Upplus. What kind of upplus will it be? An upplus is simply the weight of the fluid that will be displaced. or the amount in terms of force, the amount of fluid or water that will be displaced. So now you are swimming, alright? Now your body displaces an equal volume of water. The volume of your body is the amount of water that will be displaced. Alright? Now, if that amount of water displaced, alright, are you getting me that, is equal or more than your own weight, then you are suspended. Alright? But if you displace something lesser, I would think, something lesser than your own weight, the amount of water lesser than your own weight, you will sink inside the water. Do you understand? So that is why a ship is constructed in a way that it displaces so much water that will have more than the weight of whatever is on the ship. You understand that? So the ship is created or constructed so that it has enough buoyancy. You understand what I'm saying, okay? So if you see that question, now that question is very tricky. You can say, if you don't give us other information about the letter that was suspended. See, all you need to know is the volume of the water that will be displaced. The volume of what? The water that will be displaced. And once you know the volume of the water that will be displaced, then you convert it to what? Your force, okay? The weight. Okay, so let's do that. So since we are looking for volume, right? So let's look at it. Volume is equal to area times length. Is that not? Okay, now let's go back to the question. What was given? It gave us what? The water of what? Density. So the density of water is 1,000 kilograms per liter cube. Are you with me? Are you with me? So can we get volume from this place? Yes, we can. So what would that mean? That would be what? Density is equal to volume over mass over volume. So volume is now what? Mass over what? Density. Can you see that? Alright? I will clean up. Remember, what we are looking for is what? The volume of the water displaced. Now, if you look at this question completely, there's something else you need to note. That mass, in this term, mass, what will mass be? Mass is the volume, density times volume. Sorry, density times volume. Can you see that? Mass plus multiply density times volume. And the weight, weight, okay? You know, weight is force, right? Which is mass times acceleration into gravity, right? So weight will have the what? Mass times acceleration to gravity. If you put this one here, that will be what? Can you see all that? Can you see all that now? Right? So we are looking for the weight of the fluid displaced, and you know about the volume. If you put this one in the volume, what will it be? That will be what? That will be what? Rho AL then G. Can you see that? So now, do we have all these parameters? Yes. We have the density of water as what? 1,000 kilograms per liter cube. Okay? Then we have the length as 0.2 and G will be 10. Okay? G will be 10. So just remain the area. Okay? Right? Just the area. I want to make sure. I think I know what I need now. Sorry. You know. Now, can you look at the question? I know that some of you discovered it earlier before I did. You can see they said cube. And one of the sides of the cube is 0.2 meters. Okay? So since we are talking about cube, it means that the volume is already given, right? So for cube, it is what? L raised to power 3, right? So that would be what? 0 point, right? L raised to power 3. So this one, we are no longer using AL, right? Just say L raised to power 3, right? So what we have? The weight is what? The density is 1,000 times the L. L is what? 0.2, I mean. So 0.2 raised to power 3 times 10. Acceleration to gravity. So what we have now? So that would be what? This is more like, okay, let me complete this work here, up here. Now, this expression is more like weight is 1,000 times 2 over 10, right? 0.2 is 2 over 10, so 2 over 10 is per 3 times 10. So what we have? 1000 times 2 raised by 3 is 8. 10 raised by 3 is what? 1000 times 10. So what we have? 1000 times 1000. 8 times 10, that is what? 18 liters. Okay? I think you understand it. 8 times 10, that's 18 liters. Remember, the bedrock is what? That a cube is what? A shape that has all sizes equal. Alright? All the sizes are equal. All the sizes are equal. So you can see 0.2. You can be able to calculate your volume of water cube just by having 0.2. Are we there? So now, let's answer the next question, okay? Now the next question, we have that what? The relative density of the acid in a car battery can be measured with a what? Now, what do they use to measure relative density? What do they use to measure relative density? I think I should leave that. That's a very simple question. Just expect this in them. Okay, after that, alright, what is used to measure what? Relative density. Meanwhile, you should know that the battery of a car is, the power or the voltage of the battery of the car, are you getting it? Or to determine whether it is fully charged, we use density of the acid or the base inside to determine whether it's fully charged or not. Are you getting it now? So there is an instrument, you cannot determine the instrument. Okay, likewise number 4, we have the relative density of the powder substance can be measured using a beam balance and a what? Now when we come to powder substance, what do we use to calculate the relative density? I put this question down here because you should be what? Familiar with this question. Perhaps when you come across it on the day of the exam, you are able to answer those questions. Okay? Now number 5. The specific gravity bottle of mass 20 grams weighs 28 grams when filled with water and 30 grams when filled with what? The liquid. The relative density of the liquid S the relative density of what? S is. Now we are looking for the relative density of S. What is S actually? The specific gravity bottle of mass what? 20 grams weighs 28 when filled with what? Water. And 30 grams when filled with what? Liquid S. So S is the liquid. Now, if you are looking for relative density, just like what we did before, we say relative density is when you compare the density of substance over what? The density of water. Now, in this case, all you need to do is you calculate the weight of whatever is liquid, alright, whatever you have. So you calculate the weight in liquid, or the displacement in liquid, or the uploss in liquid over uploss in water, okay? That will give you relative density. So let's look at it. Relative density of liquid is what? Uploss in liquid in S over what? Uploss in what? In water. So what does uploss mean? Uploss simply means the force, the upward force, the amount of what? Fluid displaced, okay? Now look at the uploss very well. This is what it weighs ordinarily. A specific gravity bottle of mass 20 kg weighs 20 grams when filled with and 30 grams when filled with. Oh, sorry. We are not looking at uploss. Okay, please, sorry, I didn't look at the question properly. We are not calculating uploss, okay? But this is a formula to calculate uploss. That is when you are measuring the weight of substance inside different liquids. But in this case, what we are doing is we're going to measure the weight. Listen, the weight of what? The liquid over the weight of equal volume of water. Weight of liquid over the weight of equal volume of water. So, relative density is also what? Weight of liquid over what? Weight of what? Of equal volume of water. Okay, so what is the weight of liquid? That's what? That's what? 30 minus 20, right? So 30 minus 20. Why 30 minus 20? Because the weight of the bottle when it is filled is what? 30. But the weight of empty bottle is 20. So 30 minus 30 will be the weight of the liquid. Now, when it is filled with water, is what? 28. So, the weight of the equal volume of water is what? 28 minus 20. Can you see that? 30 minus 30 will be 10. 28 minus 30 will be 8. And that will give you what? 1.8 in 20. How many is that? That's 2. And 8 in 40, that will give you what? 5. Okay? So 1.25. Now, take note. Relative density does not have units. Relative density does not have units. And also, relative density is also known as specific gravity. It's also known as what? Specific gravity. These are things you should expect in that question. Okay? Now, let's look at the next one. Okay, these are the correct options. Okay? And let's look at the next one. When the following has the highest surface tension. Which of the following has the highest surface tension? Now, what is surface tension? Surface tension is what? Is the property of the liquid that makes it behave like an elastic spring. So that means when a liquid tends to what? For instance, if you've seen water before, you see that there are some insects that move around, on top of the water, right? Now they are able to do that because of relative density. Alright? But if we have other things on that water, they will not move. Why? Because they will sink. I get it. So, relative density is just, what do you call it? Surface tension is just that property of a liquid, alright? That keeps substance afloat. Alright? It's also part of it, okay? Alright? So, now, in this case, if we have hot water, the surface tension on the water will be broken. Now, listen, the proper definition, alright, in terms of physics of that surface tension is that surface tension is sufficiently defined as the force per unit, per unit length of the surface of the liquid in either side. You get that? The force that is acting per unit length on the surface of what? A liquid on the two sides. I get it. So it's like force over 2L, right? Force per unit 2L. You get that? That is what surface tension. These are formulas that you can use to calculate surface tension. Meanwhile, we are now looking at what are the things that have high surface tension. From this option, which of them have the highest surface tension? Let's start with the last one. Soapy water. When you put soap inside water, it destroys the surface tension of the water. Alright, so that if you put other things, it will sink. For instance, when you have detergent inside water, what happens? It helps you to dissolve some germs in your clothes, right? Germs that you will wash with ordinary water, it will not come out. Next is dirt that you use ordinary water to wash and they will not come out. When there is detergent inside that water, what will happen? That dirt will easily be washed away. Why? Because of surface tension. The surface tension is what? Greatly reduced when you have what? Just ordinary water, but when you have detergent. So now when it's soapy, that one is out of it. Oily water, you understand? So oily water has lesser surface tension. Hot water, of course, hot water has lesser surface tension. But when the water is cold, this is the one with the highest surface tension, okay? Please take note of that. That is not the answer for that number 6. Now let's go to the next one, which is number 7. Now a body which weighs 50 liters in air displaces 3.7 kilograms of water when partially immersed in water. The options on the body is, now watch. Want to look at this aspect is under principle of flotation, alright? Principle of flotation. Now look at it. A body which weighs, alright, the normal weight in air is what? 50 newtons, alright? Alright, but it displaces 3.7 kilograms of water when it is partially immersed. So weight of water displaced is what? 3.7 kilograms, which is also what? 37 what? Newton. Can you see that? I hope you're with me. You just multiply with 10, so that I get 37 Newton. Are you with me? Good. Now, in the water, the oculus on the body, very simple. They're looking for oculus on the body, right? So, if this thing is weighing 50 Newton in air, then you now immerse it in water, you now weigh it as all like 37 Newton. How many weight have you lost? It has lost what? Lost in weight. Lost in weight. Indicated as oculus. Are you with me? So it has lost 50 minus 37. So that is what? 13 Newton. Can you see now? So this is oculus. Oculus simply means loss in weight. This is a better definition for oculus. I hope you understand that, right? So that question is very simple. That's 13 Newton. Can you see the answer there? Now, a very, very interesting aspect of all these questions is number 8. So let's look at this. Look at the diagram here. And the question is the pressure exerted by the what? Trapped air in the diagram above when atmospheric pressure is 17. So atmospheric pressure, alright, let's say PA is what? 76 centimeter mercury. Alright? Now watch. Did you observe something? Look at the trapped air here. The trapped air is here. And you know, because this air is open, the atmospheric pressure will be acting this way. Are you getting it now? So atmospheric pressure is acting this way, meanwhile the trapped air is also forcing it. So atmospheric pressure is trying to force the mercury trap. You know, this is a new tool. A new what? A new tool. Alright, not a new tool where I'll post this video, like new tool. Okay, we use it to measure, alright, the pressure of gas, you know, it's part of manometer. Manometer is the whole setup. Alright, so look at this. Now, this trapped air will be forcing the mercury up while the atmosphere will also be forcing the mercury. So what do you think? You know there will be a plus and minus, right? The one that is bigger. Are you getting it now? So we're now looking at what will now be the pressure of this trapped air. So it's very simple. All you need to do is check the difference between the height of the mercury here and the height of the mercury here. So what is the difference between the height of the mercury? That will be what? 12 centimeter minus 7 centimeter. Can you see that? That's what? 5 centimeter, right? Now, the difference between the height of this mercury is what? 5 centimeters. Are you getting it now? So, what does that mean? That means that this air, you know, we are looking for. Look at me very well, look at me. I want to explain this in the way you understand it. If the atmospheric pressure and the pressure of the gas are equal, the pressure of the atmosphere and the pressure of the trapped air or gas are equal, what will happen? They will be balanced, right? The mercury here and the mercury here will be at the same level. So of course, you have pressure here, you're supposed to have pressure or, you know, equal. Are you getting me now? Now, if they are not balanced, it means that one is more. Are you getting me now? So which one is more? The one that is more is this one that is, you know, 7 centimeter. The pressure here, which is atmospheric pressure. So atmospheric pressure is 76 centimeter per mercury, right? Or 76 centimeter mercury. Now, you see the atmospheric pressure is more than this one. So what will now be the pressure of this one? So that one is very simple. All you need to do is say 76 minus the difference between their what? The height. So 76 minus 5, that will be what? 71 millimeter mercury. Oh, sorry, centimeter mercury. You just have to calculate this, alright? Okay, so this is the last question, and I hope you understand, you know, some of this concept, the density, relative density, oculus, you know, principle of flotation, and you know, applying the what? Gas pressure using your manometer on YouTube. Are we there? So let's solve more questions on another topic. Thank you.